Two powerful laws describe how electric currents create magnetic fields: Biot-Savart law and Ampere's Circuital law. But what's the difference? Hi, I am Pankaj Sharma, and in this video I will decode the difference step by step. Biot-Savart law gives the magnetic field produced by a tiny segment of a current-carrying conductor. Ampere's Circuital law tells us that the total magnetic field around a closed path is proportional to the total current passing through that path. Biot-Savart builds the field bit by bit, while Ampere's law works when symmetry fits. Both laws describe the same physical reality: how moving charges create magnetic fields. Ampere's law is just a simplified version of Biot-Savart, used when geometry is friendly. Now let's test both laws with a practical example. Suppose we have a finite straight wire of length L carrying a steady current I, and we want to find the magnetic field at a point P nearby. Can we use Ampere's Circuital law here? Unfortunately, no. Ampere's law works only when the magnetic field has a consistent direction and magnitude along a closed path, like around an infinite wire or inside a solenoid. But here, the field varies at every point, so symmetry is lost. Ampere's law works beautifully only when the magnetic field has perfect symmetry. Around an infinitely long wire, the field lines form perfect concentric circles. Every point on a circular path is exactly the same distance from the wire. The magnetic field strength and direction are identical everywhere. For the infinite wire, the field is tangent and equal all along the loop. The line integral of the magnetic field B around a closed loop is equal to the permeability of free space, μ0, times the total current I enclosed by that loop. For the finite wire, field direction and magnitude change continuously. Ampere's law can't simplify the integral anymore. Here's where Biot-Savart law saves the day. It lets us compute the magnetic field from each tiny element of current and then add them all up. That's why Biot-Savart law is more powerful. It doesn't depend on symmetry. You can use it for finite wires, circular arcs, or irregular shapes. Anywhere Ampere's law falls short. Thanks for watching. For more physics concepts made simple, don't forget to like, share, and subscribe to Brainleague Learning.